Kotriwal. I work as a senior software engineer at the search platform team at Uber.
Hello, I'm Aparajita. I'm a senior software engineer at Uber. I've been in search platform team for about 2.5 years now. Thank you for attending so far. This is the last session for the day. I hope this session is insightful for you guys. Thank you.
We work as a large distributed team. We are the two lucky souls presenting up here today, but we are thankful to all the team members across Bangalore, Sunnyvale, San Francisco, and Seattle. So setting up some context here, search serves several critical use cases at Uber. So if you are ordering food on Uber Eats, or if you are booking a cab, there is search engine underneath. And the search ecosystem at Uber has evolved over the years. So you can think we had Elasticsearch systems, we still have. We have ES 2.0 in some systems as well. We have an in-house search engine that we modified heavily on Lucene that introduces the in-memory layer and that allows quick search. So it's a different data structure from the Lucene index itself. And then we have the Lucene NRT segment replication-based systems. And last year or so enters OpenSearch. So with OpenSearch, our aim is to make it a standardized search platform, use all the learnings across the years from operating different search engines, and offer it via OpenSearch. And in the process, things that we have learned, we want to contribute it back, work with the community, and make it better for all. Now, coming to platformization, you have, like, an organization has two choices. Either they can go with a managed cloud offering, or within their own platform teams, organizations, they choose to self-host these deployments. At Uber, we have a self-hosted OpenSearch infrastructure built on top of our inbuilt data centers and public cloud compute. As I mentioned, we work across several mission-critical use cases. We power most of the Uber's business-critical use cases. As a platform team, we focus on reliability, resiliency, ecosystem integration, and we want our customers to have a seamless experience. Now coming to the ingredients of what makes a good platform. So we have an in-house custom fork. So it's an OpenSearch on GitHub. We have our own custom fork. We've committed to that as well and contributed back. Once you have the code, you want to build it, deploy it, and roll it out. So we have deployment safety, tiered rollouts, and zero downtime upgrades. We have infrastructure resiliency, so we have two regions. One goes down, other keeps running. Within regions, we have zones that are rack aware and all sorts of infrastructure resiliency in that place. We have rich integrations with in-house data systems. So we work heavily on Hadoop file systems, Spark, Kafka, Flink. So we want our customers to just plug and play their indexing, searching things, and just breeze it through. Integration with in-house security solutions, L4, L7, authentication, encryption. Observability, if you have a cluster, you want to know fine-grained details of how the cluster performs, how an index performs, how the coordination logic is going on, and everything inside it. And then the community collaboration is also a vital part. We are working with community on pull-based ingestion, gRPC support, cloud-native architecture, and many more. So this is a high-level map of OpenSearch at Uber. We will zoom into different components as we go through our slides. So as I talked, we have an open internal fork, we have a release pipeline, we have a security ecosystem, we have an observability stack, the data ecosystem, and the resiliency side of things as well. Handing over to Aparajita.
Hey everyone. So I'll be mostly be covering how we create a custom extension role-based plugin. What all the challenges that we faced when we were trying to accommodate Uber security solutions with the OpenSearch features. So before that, I'll give a brief around how in Uber we build a specific version of OpenSearch and how we deploy those builds across thousands of nodes at Uber scale. So just a quick background before we start. Since past 1 year, Uber has started to heavily adopt OpenSearch, and we have moved from 2.13 to 2.19 right now, and 3.3 version release is something in plan. OpenSearch version release itself is quite fast paced, so once in every 1 or 2 months there is a new minor version release. In Uber, we want to follow that, have that same pace to ensure that all the features that OpenSearch provide, Uber are in sync with that. So with that, let's start. So how do we start? We start with keeping an internal fork of some of the OpenSearch open source code. We manage around 20 plus plugins. Some are custom, some are standard, some are just custom adapted just for Uber. Now these plugins get combined with the core OpenSearch. We leverage OpenSearch build tool, which is again an open source project, and we have a manifest file which I'll show you in the follow-up slide that depicts that how we ensure by making a build that all the plugins are of the same version as the OpenSearch to make sure we don't run into a compatibility or build issue when we are creating a OpenSearch build. So the whole purpose of this OpenSearch build tool is to install all the plugins to the OpenSearch core build and uploads that to the Uber Artifactory. Then we have another service called Uber Wrapper service, we call it differently, that does some custom installation like configuring paths for the plugin or OpenSearch where the config file will be mounted in the Docker container, resource allocation, JVM settings, logging settings, and some snapshot related configurations. So what this OpenSearch wrapper build service does is it downloads the artifactory from the tarball from the Uber Artifactory, does some custom installation, and then we create a binary which is ready to be deployed on thousands of OS container at Uber. Now, just a quick glimpse on how our manifest file look like. You will see some of the like OpenSearch, you will see that we keep an internal fork of the OpenSearch open source project, and some of the plugins you will see we directly fetch from the OpenSearch GitHub repository, and we ensure that whatever OpenSearch branch or tag that we're building, the plugins are of same version. We derive the same the version from the OpenSearch file itself and make sure that version controlling is there and plugins are of same version as the OpenSearch. Yeah. So now that our custom plugins are built, so custom binaries are built, getting it out safely across thousands of nodes without breaking a thing. So that is where a release pipeline comes in picture. So what does release pipeline do? So like any other organization, we start deploying on gating instances first, and we roll out an ephemeral storage instance, a temporary instance where we create a dummy instance, and we have a set of search queries that we fire on the dummy instance to see the availability of the nodes, and we do a bunch of more regression testing, and then we proceed to the production. And in the production, as we follow towards, we have this tier-based rollout. Tier as in we start from the lower criticality one and slowly move to tier 0, which is a higher critical use cases. And within tier, we do instances roll out in batches. So as we move forward from one tier to another, we have a soaking time which also varies, also increases as we move towards a higher critical tier use cases. Now, with each tier, we start with regional deployments so that it fades across different data centers and cloud zones. This is to limit the blast radius, so if something goes wrong, and we also have this a counter policy at our instances that makes sure there is no continuous rollout, any other operation that is happening at the low node level. Now, we have alert configured at all of these steps. Before that, now at each node, when we take down a node, we have pre-hook and post-hook installed. So before we get down a node, we have a flushing operation and bunch of other operation, like we change the cluster routing allocation from all to primaries to ensure that the node, the replica shard on the node, replicas doesn't show unnecessary shard movement. And once the node is updated, similarly, we undo that when we have post-hook operation to revert that routing allocation from replicas back to primaries back to all. At all of these steps, we have alert configured both at instance level, region level, and node level. So let's say in case CPU utilization go high, node or instance is experiencing high latency, the OS cluster is in yellow state, the node itself is in error state or not coming up. Let's say the node, the shard relocation was stuck for long. So at all these steps, we have alert configured. At the moment the alert fire, we pause the rollout. And this is how we do the end-to-end deployment across all the Uber instances. this whole release pipeline has actually quite been effective in past few instances where we have found a buggy release early at the very early stages of the deployment. And at all these steps, we also have a pingless service which continuously does the pingle dummy write, get and put operation to ensure the availability is intact for all the Uber instances. So this is the overall picture how a release pipeline works. Now, when I say release pipeline, it is not just the OpenSearch that we deploy alone. The OpenSearch node consists of several other containers as well. So OpenSearch doesn't run in isolation, and it's composed of several other components running on the single host. So we have data and master node. We also have a worker container that's like a sidecar container that actually syncs the goal state, actually syncs the actual state to the goal state. So imagine you have an instance and you have a custom configuration at instance level. So someone runs change the configuration at instance level. The job of this worker is to continuously ensure that the node goal state is in sync with the actual state. So it changes the node actual state to be in sync with the goal state. Apart from that, we also have Nginx that does reverse proxy request sanitization and stuff. We also have a matrix exporter that is running that continuously polls the matrices that is emitted by the OpenSearch and publishes them for monitoring purposes. Apart from the data node and master node, we also have a client node which hosts the OpenSearch dashboard. So the same release pipeline goes in picture when we say we deploy during a release pipeline. All the container deployments are also done with the release pipeline. Now, moving to the security. So as I mentioned in the previous slide, we have created our own custom extension role-based access plugin, which is a combination of OpenSearch feature and some of the organizational level security offerings that we have at Uber. So we'll see how end-to-end client-to-server communication are secured, including the data. So before that, this is how our architecture look like. So we have OpenSearch cluster. Data node, master node mostly communicates to each other using the TCP protocol, and we have some services in Go and Java that calls the OpenSearch service. The Muttley that you see, you can consider is like a in-house Uber in-house load balancer. That's some external extension operation apart from load balancing, like rate limiting circuit breaker. We have some UI services which directly call the OpenSearch cluster. The UI we use Cerebro, which is a legacy UI dashboard that we have been using so far. And we also have dashboard, OpenSearch dashboard that calls the client node of the OpenSearch cluster. We have clients directly calling the OpenSearch cluster using the curl command, yap command, studio command. We have Spark job, which we use for batch ingestion, and also during the index creation for like bulk writes and updates we do using the Spark job, which directly writes to the cluster. And we have starting to support multi-tenant architecture in OpenSearch cluster, as in a node can have multiple indices belonging to different tenants. And with all these, we want to ensure all the communication from server to client, client to server are all encrypted, are all secure. One tenant should not be able to see or operate on the index of the other tenant. So this comes to encryption in transit. So we have a platform level baseline offering which we call secure proxy. This data plane encrypts all the internal traffic as well as authenticate and authorizes all the connections. The data nodes communicate to each other as well as master node using the TCP protocol. So on each node, the red boxes that you will see are the secure proxy that we run on. We can assume it to be like a L4 MTLS secure proxy. This secure proxy establishes an encrypted connection with all the peers destination secure proxy. The destination secure proxy applies authorization on all the inbound requests based on the client certification. Now, if it allows the destination secure proxy allows the TCP connection to pass through, otherwise it denies. Now, this is not only at the TCP level, we have same at the HTTP level as well. And with OpenSearch 3.0, there are a couple of bunch of APIs that have been supported through gRPC. the same secure proxy would be used for all the gRPC connections from service to the OpenSearch cluster. Now this ensures all the data transferred from client to server are encrypted in transit, and at Uber we also have by default all nodes are encrypted at rest. So encryption at transit and encryption at rest is something that we come with Uber security solution offering by default. Now before I go into where we were previously on L4 and how we migrated from L4 to L7, how we created our own custom plugin, just a brief on so that everyone knows that what is L4 and L7. L4 is like a coarse grained permission, network level permission. You can assume in this context to be you are saying all the given services that can call, authorizing all the services that can call your service. L7 is more fine grained application level or API level control, where you say what all APIs other services can call for on your service. So previously OpenSearch was on L4 and we started to move to L7. So without L4, this was, I think something changed. Okay, sorry about that. So previously OpenSearch was on L4. So this is how our architecture looked like. So the L4 secure proxy that I was showing you in the previous slide gives the L4 auth. So all the blue color things are L4. So that says that all the services that are allowed to call the OpenSearch cluster. And then we have, so if any, let's say a client gives a request to OpenSearch cluster, before via any service, before the request actually being served by the OpenSearch cluster, the service sees OpenSearch cluster, secure proxy intercepts in between and see is these service 1 or service 2 are allowed to call OpenSearch cluster or not. So if yes, allow, if not, deny the request. Now all the services who are allowed to call the OpenSearch cluster can access almost all the API. So we started with implementing L7 at the calling service layer. So we have L7 at the service 1, service 2. And so any call that comes to service 1 or service 2, we see that if this person, the customer who is clicking any API, let's say delete index or write index, does this person have the access to execute read or write API on the OpenSearch cluster or not? Now this was working fine till we realized there are more and more services and instances where people and service wants to call the OpenSearch cluster directly. So we started with having our security plugin in picture. Now with this, we wanted all these services which were previously calling OpenSearch cluster to pass this short-lived token, service token, person token to the OpenSearch cluster. So we propagated all the short-lived token from all these services to the OpenSearch cluster. Now what our plugins does is, this looks something like this part. So Uber also have a centralized access managed policy, which we call charter policy. You can consider it as similar to Google resource, AWS IAM or Google IAM. It's a combination of permission and association, where you say that any resource can be an instance, can be an index, have that action permission, action as in read, write, admin operation, the group service, a service or group or LDAP has permission to do any action on a resource or not. So let's say you want to trigger any write index on the test index. So what our plugin does is, our custom plugin intercept all the HTTP requests, and with the HTTP request we call our own customized Uber charter policy, saying that the client is trying to access resource test instance, and within the test instance it is trying to access test index. So does the person or user belong to test group or test service, so that they can do write operation on the instance and index or not? If yes, allow, if not, then deny the request. Now we have similar thing that we follow for multi-tenancy as well. For each multi-tenant will have their own separate index, so the same resource path works. Also we have multi-tenant's name on the resource path added, so that we can authorize using the Uber policy. So this is how we have a security solution at Uber, including encryption in transit, encryption at rest, L7 added, and yeah, that's pretty much it. And I'll pass it over to Anand for covering the ingestion part and the migration challenges that we did.
And thank you. So we saw the security part, the build integration pipelines. Now you have a cluster, you want to ingest data. So how could you do that? So roughly there are two modes: batch ingestion. So you have a source of truth, terabytes of data maybe, and you want to say, build me a search index for it. And we want to build it as fast as possible and in a performant way, high throughput. Or you have a real-time ingestion. You say, I have an event level granularity of updates coming in. I want these to be reflected in the search index. Or you could have a batch plus streaming mode where you say, I have a batch index, I have a streaming solution. You ensure that I have the latest updates, versioning of deletes, and all those things that come into it. So I will talk about these things, how we solve it for our customers who use search platform OpenSearch offering. So coming to batch ingestion. So as I mentioned, we have a Hadoop file system. We use it widely at Uber. We use MySQL Cassandra. Users have the data in these data stores, and they want to build a search index, and we want to help them build it as quickly as possible and as seamlessly as possible. Enter Spark. So Spark is a distributed processing engine. I think you must be aware about it. So it efficiently builds. You can parallelize things. You can read in parallel, repartition, and do things over it. An interesting thing or an important thing is the OpenSearch Hadoop. So it's already a part of OpenSearch ecosystem. It's a project that exists out there. It provides you read, write integration along with all sorts of mappers, serializers, config tuning, batch size tuning, retries, HTTP retries, endpoints, and everything. So it exists out there. We build it. Our workflow that you see on the right is an orchestration workflow. You could think about like AWS step functions, or we call it Cadence internally. It's open source. What it does is it triggers a bunch of steps. High levels is it reads data source, validates the schema. We have two regional deployments. So we trigger we ingest in the two regions. We do index validation, and for a seamless switch, user just create an index and read from an alias. So when the index is ready and they have validated it by shadow traffic or by a Lucene index validation tool that we have, and they can just switch the indexes. So efficiently takes care of building of new indexes from source of truth, switching the production traffic. All of it happens as part of the workflow. And workflow has knobs to do other sorts of things like blue-green deployment and other things. One interesting thing is OpenSearch 3.0 has gRPC endpoints, and gRPC is quite performant, especially for high throughput ingestion. And we have been seeing good improvements like in our Spark ingestion throughput and the time it takes to ingest a large amount of data. And hopefully we are going to work and try to have this endpoints also supported in OpenSearch Hadoop. So I talked about batch ingestion. I will just go over a case study. So we had one OpenSearch customer team that wanted to ingest 1 billion scale vector, 2,000 dimensions, and all sorts of scaling challenges that come with it. So OpenSearch is a great vector database as well. It provides you different data structures, IVF flat, HNSW. There's a FIS library underneath it. There is a Lucene engine underneath it. And the recall is good and the performance is good as well. But with 1 billion scale vector ingestion, we started running into a few challenges, so I will go over them. So one of them is throughput. So all these vector indexing are very CPU intensive processes. So underneath you are building HNSW graphs. They spike up your CPU, they use your memory a lot. And what we started seeing is we wanted to saturate our CPU so that we could index as fast as possible, and also wanted to have the cluster reliability in place. So we did not want cluster going into a red state, leaving the node leaving the cluster, and reliable in all aspects. So some of the things that we did was we tuned the Spark parameters to have maximum CPU utilizations. So you have executors in Spark and you have number of cores per executor. So you multiply them, you get number of vcores. That is what is the parallelization that you achieve. So we try to saturate that. Then there is the number of partitions of your data. So ideally, we started with the same partitions as the number of executors, but then we 2x, 3x'd, and we found out that having more partitions at around 2 to 3x is much more better, because there are some cores that are stragglers. They are going slow. So they pick up and you end up ingesting faster with those. Then there is tuning Lucene indexing policy. So creating a lot of small segments is not recommended because they add the disk IO. They have an implication on the merges taking longer. So we tuned the merge policy to reduce the number of segments, the floor segments. There's a config that controls the number of segments and the size of the segments. So we tuned those. We disabled auto refresh, and yeah. So apart from it, there are other bunch of things we did. We reduced mapping size, like you have stored fields or doc values enabled by default. We did not need aggregations. We just wanted it as a we just wanted it to have a text features and vector features. Vector indexing is memory intensive, so vertically scaling also helped a lot. And what took 12 hours, we got it down to 3 hours. Yeah, and all these optimizations made our jobs faster. The customers team could run it, get their whole 1 billion index done. An interesting thing to note here is that we are saturating CPU, so we separated the serving layer from the ingestion layer. So we did a blue-green deployment. So what it essentially means is while the ingestion goes on, there is another cluster serving the traffic. We quickly ingest into the new data or the refresh data and switch over traffic to the other cluster. So that's what we did for the vector scale. I will now move to the real-time ingestion side of things. So we talked about batch ingestion. Now you have event level granularity of data that is coming in. And how do you ingest it? So Kafka is a very popular, that's the de facto async channel at Uber. So we have something called Kafka consumer proxy. So if you see here on the left, there is a Apache Kafka cluster, and there is a consumer proxy. That's a service that tells you, hey, I will go and create a gRPC endpoint on your destination service. That's on the right. And for each message that you receive on Apache Kafka cluster, you basically call that endpoint. So it's a sync call. So for each message, these blue boxes fetch. They call the gRPC endpoint on our destination consumer service, which basically indexes into OpenSearch. So this is a whole sync call that happens from Kafka to the end-to-end. So, and we productionized it. This works well. But then there are limitations to a fetch versus a pull-based ingestion. So enter OpenSearch 3.0. What essentially ends up happening here is the OpenSearch clusters pull it from the Kafka channel. On the right, you see the settings for those. So you basically define an ingestion source. It could be Kafka or Kinesis. And you give the pointer. That's the offset where you want to pull it from. You give the Kafka clusters destination address. And then you give it works in segment replication mode. So it doesn't work in doc replication mode. And the important part to note here is you can efficiently, gracefully handle back pressure and pace control of your data ingestion. In the earlier mode, you had no control over your clients pushing data to you, and that could lead to unavailability scenarios, burst of traffics, and your cluster being in a red state or unreliable state. With pull-based, you control the ingestion, you have graceful back pressure handling, and this was a feature that Uber engineers worked with the OpenSearch community, and it's released as an experimental feature in 3.0. We are using it widely, and we plan to add to it. So the ingestion story was still here. Now it's the observability stack that we have. So you have OpenSearch clusters running. You want to get granular details. How is your indexing doing, searching doing? How is your cluster state? How is your master coordination logic going? How is your leader election going? All sorts of things. So there are two parallel modes of metrics ingestion that we have right now. One is the Prometheus exporter. So OpenSearch has a cluster node indexing and stats API. So you call that endpoint, it gives you a list of returns, returns you a bunch of JSON that says a lot about the cluster stats. You scrape it, Prometheus pulls it, and it goes to M3DB. M3 is our time series database. So that is where all the metric points flow through. But this has a downside. So if you see, this is just a scraping based methodology. It does not provide you granularity what's happening at index level, at a search request level, at a coordination logic level, and it doesn't have statistical functionalities like P99 and other things that we want. So what we did is we had a metrics plugin that builds on top of the classes that metric plugins provide, intercepts the requests, all the search requests, the indexing requests, the coordination requests, and this client basically then completes the loop of pushing it into M3DB and gives us all the metrics that we want. So yeah, just going a bit deep into the plugin interaction. So as I mentioned, Prometheus relies on stats API, does not give real-time visibility. So we had this metrics plugin, and the three classes are action filters, operational listeners, and the transport interceptors. So these are basically interceptors. You get a request, you start a timer, you put some tags into the metric, and you can then filter by those tags, do all those aggregations on those top of those tags. So action filters are for indexing and search request, transport interceptors are for the coordination request, operational listeners are for the underneath the shard movement and the operations that happen on the OpenSearch cluster. Yeah. So this was the observability story for OpenSearch that we built. I will just briefly talk about the migration story as well. So we had scores of Elasticsearch clusters. We have moving them to OpenSearch. We had on as old versions as 2.0, terabytes of legacy indexes. We ran into backwards incompatibility. But yeah, we are moving all of them to OpenSearch. The migration approach, I talked about the ingestion toolings that we have built. We have built the Spark ingestion. If customers have their source of truth, we just re-index, run the Spark job, get the index, do the validation tooling that we have, shadow it, and gradually cut over traffic. So this has solved 99% of our problems. And yeah, most of the users have a source of truth, so we just re-index from that. Migration wins, I mean, we have a lot of migration wins, but the first is latency. I mean, that impacts your end customer if they're seeing the results faster, win-win. Better reliability from features like adaptive replica selection. So this was this was a big pain point in old ES system that we were running. So if one node is struggling or it is having performance issues, ES wouldn't, or it wouldn't isolate that node. Now we have that feature, and it has made our clusters more reliable. Lucene library has seen improvements, scores of improvements. So you get better indexing, query performance. Lots of migration wins, just calling out the majority of those. Yeah, that's it from me. If any questions, yeah.
Thanks, very informative. I had a question on the encryption at rest and encryption in transit. So when you do the encryption at rest, is it you bake your underlying nodes with something, or how are you doing that part?
So on every host, we have a secure proxy, which is an open source version of Envoy that is running. So all the outgoing calls that goes outside the cluster or on the node, we encrypt that, and that ensures that all the calls after going outside the node are encrypted.
Right, so that's the one transit. What about encryption at rest? How are you doing that?
Encryption at rest is something that we have by default. So every time, that is something that we support through LVM. So every time, this ensures that all the unmounted disk or drives that we have that are already encrypted. So if you ever get hold of the physical device, physical hard disk on you would not be able to decrypt it. So until the disk is mounted, till that time there is no encryption at rest. That's when you remove that, unmount it, that is when you will not be able to decrypt it, is what we have.
Do you use just LVM or using DMCrypt or anything on top of it?
No, it's just LVM as of now.
Thanks.
Any more questions? No? Thank you. Thank you.
Thank you.